For generations, humanity has chased power. From the crackling fire to the roaring furnace, our progress has been fueled by an insatiable appetite for energy. But this relentless pursuit has come at a cost etched into the very fabric of our planet. Climate change, resource depletion, and geopolitical instability. The shadows cast by our current energy systems grow longer each day. We stand at a precipice, searching for a solution that is clean, abundant, and safe. What if the answer isn't a radical new discovery, but a forgotten element, quietly waiting in the Earth's crust? An element so potent that just 1 kilogram of it could unleash the energy equivalent of 3,500 tons of coal. This is the story of thorium, an energy system that could fundamentally change everything. Our modern world runs on power. From the device you're watching this on, to the hospitals that save lives, and the factories that build our future, every facet of our existence demands a constant, reliable supply of energy. Today, over 80% of this energy still comes from fossil fuels, coal, oil, and natural gas. These carbon-intensive sources are not only finite but also the primary drivers of greenhouse gas emissions, pushing our planet towards irreversible climate change. While renewable energies like solar and wind offer a cleaner path, their intermittent nature presents a significant challenge for providing the continuous, baseload power that modern societies require. The grid needs stability, a constant hum of electricity, day and night, rain or shine. We are in urgent need of an energy source that is powerful, clean, and capable of operating continuously, without devastating our environment or depleting our resources. So, what exactly is thorium? It's a naturally occurring, slightly radioactive metallic element, named after Thor, the Norse god of thunder. Discovered in 1828 by the Swedish chemist Janus Jacob Berzelius. Thorium is found ubiquitously in small amounts in most rocks and soils, particularly in minerals like monazite sands. It's approximately 3 to 4 times more abundant in the Earth's crust than uranium, the fuel for most of today's nuclear reactors. Unlike uranium-235, which is directly fissile, meaning its atoms can be split to release energy, Thorium-232 is fertile. This means it cannot fission directly. Instead, it must first be converted into another fissile material. This seemingly minor difference is precisely what gives thorium its unique and potentially revolutionary properties, setting it apart from the nuclear technology we've known for. The magic of thorium lies in its nuclear fuel cycle. When thorium-232 is bombarded with neutrons, absorbs one, transforming into thorium-233. This isotope is unstable and quickly decays into protactinium-233, which then over a matter of weeks decays into uranium-233. And this is the key: uranium-233 is a highly fissile isotope, capable of sustaining a nuclear chain reaction and releasing immense amounts of energy. This process, where a fertile material is converted into a fissile one within a reactor, is known as a breeder cycle. What makes the thorium-radium-233 cycle particularly elegant is its efficiency. For every neutron absorbed by thorium to create U-233, more than one new neutron is released during the U-233 fission, allowing the reactor to effectively create more fuel than it consumes. This self-sustaining nature means that a relatively small initial amount of fissile material can kickstart a reaction, and that then continues to produce its own fuel from abundant thorium. Now, let's return to the staggering comparison that truly underscores thorium's potential. Imagine the energy contained within a single kilogram of thorium. When fully utilized in a breeder reactor, the small amount of material can produce as much energy as burning 3,500 tons of high-grade coal. Let that sink in. To put it another way, a block of thorium the size of a golf ball could power a city of 100,000 people for an entire year. The implications are profound. This incredible energy density means vastly reduced mining operations, significantly less transportation, and virtually no greenhouse gas emissions during power generation. It speaks to a future where energy scarcity could become a relic of the replaced by an era of abundance and environmental stewardship. The sheer scale of this energy potential is almost beyond comprehension, offering a pathway to meet global energy demands for millennia. The thorium fuel cycle is most efficiently utilized in a specific type of reactor known as a molten salt reactor, or MSR. These are not your grandfather's nuclear power plants. MSRs offer a suite of advantages that address many of the concerns associated with traditional nuclear fission. MSRs typically operate at atmospheric pressure, unlike conventional reactors that run under high pressure, drastically reducing the risk of explosive steam buildup. The fuel itself is dissolved in a liquid salt, which acts as both the fuel and the coolant. Should the reactor overheat or lose power, a passive freeze plug melts, allowing the liquid fuel to drain into subcritical storage tanks where it cools and solidifies. This walkaway safety feature prevents meltdowns, making them inherently safer. The waste products from thorium reactors have significantly shorter half-lives compared to uranium-based fuels, decaying to safe levels in hundreds of years rather than tens of thousands. Furthermore, MSRs can be designed to burn existing nuclear waste from conventional reactors, effectively reducing our legacy of high-level radioactive material. Crucially, the uranium-233 produced in the thorium cycle is typically contaminated with uranium-232, which emits intense gamma radiation, making it extremely difficult and dangerous to handle for weapons proliferation. As mentioned, thorium is far more abundant than uranium, ensuring a fuel supply for thousands of years. MSRs can also operate at much higher temperatures than conventional reactors, leading to greater thermal efficiency in converting heat into electricity. This high-temperature operation also opens doors for industrial process heat, hydrogen production, and efficient desalination of seawater. With such compelling advantages, why isn't thorium powering our homes today? The answer lies in a complex interplay of history, politics, and technological challenges. The initial nuclear research in the mid-20th century was driven by the Cold War and the race for atomic weapons. Uranium reactors, particularly those cooled by light water, were favored because they produced plutonium, a key ingredient for bombs. Thorium, which doesn't readily produce weapons-grade material, was sidelined. While the Oak Ridge National Laboratory in the United States successfully operated a molten salt reactor experiment in the 1960s, proving its viability, sustained funding and political will for thorium research. When developing MSR technology presents its own unique hurdles. The corrosive nature of molten salts at high temperatures requires specialized materials, and the reprocessing of liquid fuel is a complex endeavor. The established infrastructure for uranium mining, enrichment, and reactor construction also created a powerful inertia against switching to a completely new fuel cycle. Public perception, often scarred by accidents like Chernobyl and Fukushima, has also created a generalized fear of anything nuclear, regardless of fundamental safety differences. Despite these historical roadblocks, thorium is experiencing a dramatic resurgence. Nations like China and India, facing immense energy demands and seeking energy independence, are heavily investing in thorium MSR research and development. China, in particular, aims to have a commercial thorium reactor operating within the next decade. India, with its vast thorium reserves, has long pursued a staged nuclear power program centered on thorium. Beyond national programs, a growing number of private companies and startups around the world are pioneering new MSR designs, leveraging modern materials science and computational power to overcome past challenges. These next-generation reactors are often envisioned as smaller, modular units that can be mass-produced, installed in remote locations, and even integrated with renewable energy sources. Thorium could not only provide clean baseload electricity but also heat for industrial processes, fuel for advanced transportation, and even play a role in space exploration. It represents not just an alternative but a potential paradigm shift, offering a clean, safe, and virtually limitless energy future for humanity. The journey of thorium, from forgotten element to potential savior, is a testament to human ingenuity, why and our relentless quest for a better future. The promise of 1 kilogram of thorium equaling 3,500 tons of coal is more than just a scientific fact, it's a beacon of hope. It points to a world free from the tyranny of fossil fuels, a world where abundant, clean energy powers prosperity without compromising our planet. The technology is advancing, the understanding is growing, and the need has never been more urgent. The question now is not whether thorium can change everything, but whether we, as a global society, are ready to embrace this thunderous power, responsibly and with foresight, to build the sustainable future we so desperately need. The energy revolution may well be written in the silent strength of thorium. Thank you for watching our video. Don't forget to like and subscribe. We value your thoughts greatly. Let us know in the comments.